Hello everyone, I'm Emma, Ecosystem Partnership Manager for Data Science Conference, and I will be there as tech support during the tutorial. I want to introduce you to our tutor, Stefan Dejanovic. He is a CTO at Gap App, and he will hold the optimizing workloads with Transformers and Diffusers tutorial. And Stefan's colleague Daniel Sorchak will help him with holding the tutorial.
Okay, thank you, Emilia. So can we start?
Yeah, and sorry for misspelling the tutorial's name.
All right, so I'll share the screen right now. Okay, so can everybody see the screen?
Yeah, we can see.
All right, so hi everyone. So for today's session, Daniel, who is PhD and ton of experience in AI, is gonna do a session with me for about optimizing workloads with transformers and diffusers. So we'll basically cover on a couple of topics. But before that, I will leave the mic a bit to Daniel so he can do an introduction of himself. Daniel?
Hi, everybody. Yeah, sorry, my mic. Yeah, so my name is Daniel Socek. Basically, I have a PhD in computer science, and I've been working in areas of cryptography, computer vision, and a lot of machine learning and AI applications as well. Currently, I'm advisor to a Stefan startup, Gap App. In addition, I am full-time engineer at Intel, currently working on optimizing AI workloads on Gaudi 2 and other Intel GPUs.
Right. All right, perfect. So we can start the session. So the topics that we will cover here is part one, which I'm going to do a bit of showcases about transformers. We're going to do a quick overview, then go to the benefits and usage, and the last thing, the case study about summarization, optimization, and demo. Basically, going through a code and seeing live how the optimization works on models. And part two will be covered by Daniel, and he will do diffusers, basically an overview what are diffusers, about the components, and do a small case study about stable diffusion optimization demo. So to start, about AI workloads optimizations, basically AI-related computational tasks and processes. Well, in the recent years, we all see, we all witnessed the surge in the capabilities of AI, and basically largely owing to the incredible strides made in machine learning models. And basically among all of that, transformers have emerged as a cornerstone reshaping the landscape of NLPs, computer vision, and various other domains. So originally introduced in a seminal paper titled Attention is All You Need by Vaswani. And they have rapidly become the, let's say, big deal in a modern deep learning architectures. And their unique ability to handle sequential data efficiently, capture long-range dependencies, and process information in parallel has sparked a paradigm shift how we approach to solve complex tasks using machine learning. And basically that's it. The examples where we can use optimizations and use transformers is definitely in training, inference, pre-training, data preparation, and feature engineering. So what are the benefits of optimized AI workloads? So definitely the one core thing is faster inference and training, because we all know that we are all limited by hardware, so we need to optimize our models and workloads so we can basically have faster AI in the background solving our tasks. Next thing is maximize productivity and resource utilization, and basically lowering our cost. So the strategies how to do that is, first thing we can do is model pruning and quantization. Basically, technique is pruning redundant parameters, so reducing precision through quantization, and that can lead to a significantly shrinking the model size without substantial loss in performance. Next thing, hardware acceleration, leveraging GPUs and TPUs that can enhance the speed of model inference. Basically, there is an example, Hugging Face seamlessly integrates with frameworks like TensorFlow and PyTorch, allowing users to basically get the power of these hardware accelerators effortlessly. Third thing is knowledge distillation and training smaller models to replicate the behavior of larger models. That approach involves training smaller, let's say lightweight models to mimic the behavior of larger. Again, we have the Hugging Face that facilitates the entire process by providing access to diverse range of pre-trained models that we can basically use as a teachers for our distillation. So we already have a bunch of pre-trained models that we can immediately start using, basically training our own models to become more efficient. And then transfer learning and fine-tuning. A little bit of basically connecting to the past knowledge distillation, utilizing pre-training models and fine-tuning them for specific tasks. So rather than starting and training the models from scratch, we can use pre-trained models and fine-tune them on a specific tasks that we can basically significantly reduce training time and computational resources. Again, we can use Hugging Face definitely for variety of basically a core resource for variety of pre-trained models, basically saving us both time and effort. So integrating these optimization techniques with the let's say ease of use offered by definitely Hugging Face, we can efficiently work with transformers and getting the power while mitigating the computational burden that we'll have. Yeah, because not everybody, we cannot have the unlimited hardware and everything, so we need to be cautious about hardware limitation and the time that all of this it takes to train the model, and definitely so we need to think about optimization definitely here. So about transformers, they are, let's say, advanced neural network architectures initially designed for NLP tasks. So the key components for transformers are attention mechanism encoder-decoder architecture. So these models boast basically encoder-decoder architecture commonly used in tasks such as language translation and summarization. One of the standout features of transformers is their ability to efficiently capture long-range dependencies and parallelize tasks efficiently. And scalability here is basically really valuable, especially when handling vast data sets, minimizing performance losses. So the examples that we have here is pretty much everything. Everybody heard about that. So ChatGPT, Bard, Llama, T5, BERT, and many more, including non-text models like VIT, and so on. So definitely the main advantages are efficient parallelization, capturing long-range dependencies, and scalability in handling large data sets. So what are the benefits of transformers? Transformers come with a, let's say, myriad of benefits that elevate their utility in machine learning. Their enhanced learning capabilities allows them to grasp relationship within data without relying on predefined structures. So additionally, their adaptability through transfer learning empowers models to fine-tune for specific tasks with minimal data. And moreover, transformers excel in understanding context and nuances in language tasks, contributing significantly to language understanding applications. So their flexibility is definitely across domains like NLP, computer vision, and recommendation systems, achieving state-of-the-art results, definitely in various benchmarks and competitions. So we're going to cover one example about benchmarking and how the using transformers are definitely, Hugging Face library optimum is definitely putting performance and giving us less time that we need to use to train the model. So we're going to see the benchmarking example as well. So how do we use transformers for a variety of cognitive tasks? So these models are, fantastic for automating tasks, utilizing natural language understanding and generation to automate repetitive process effectively. And they also can contribute to enhancing data processing pipelines, offering faster and more accurate results. So transformers basically enable us to provide personalized user experience and accurate recommendations, contributing significantly to decision-making processes in different domains. So now we can go to the showcase and go for 2 examples to illustrate how transformer-based models can help us optimize our workloads, and how can we get better performance and see that for a benchmark. So I'll go to here to my code. Now, we will not run the code here. Basically, I did run the code previously to this workshop just to get the results. You have the code in the source folder in the files that we have for this workshop, so you can try it yourself. Because bear in mind the time and everything that we need to go through, we will just go through the code and explain exactly what is it doing. So the first example would be to use task type summarization and to see how to incorporate transformers to get some better, let's say, performance regarding getting the results from our model. So here we are going to use transformers. We're going to use definitely the vanilla, basically, transformers pipeline from Transformers library of Hugging Face. And then we're going to use pipeline from Optimum pipelines, basically improved a pipeline with accelerator, better transformer. This is what we're going to use. And we're going to use it on a model, Facebook BART large CNN model. I mean, it doesn't matter, or really, I mean, you can use various different models. This is just for a showcase that we are currently using. And we are going to say, to summarize a text here and to write this a small text summary about the article. So the article that I pulled through today was about the volcano in Iceland. It's almost ready to erupt. So basically this article was from BBC explaining about Iceland and what Iceland is facing currently at the moment. So I set up the pipeline from transformers to do the summarization for this model, and this is going to be the article. So I'm going to call summarizer for this article. I'm going to catch the time and basically to see the time and print the summarizer, basically summary of this article. So here we can see the result, summary text. So from all of this article, I have the summary of Iceland's southwestern peninsula could face decades of volcanic instability, warns the Icelandic Met Office, and one more sentence about it. But it really doesn't matter for this case. So we got the summary text, and we have the time, which is 42 seconds, for summarizing this small article, right? It's quite a long. So using a better transformer here. So we're using pipeline, but this time from Optimum. And same task type, same model. We are using accelerator better transformer. So out of the box, this accelerator can basically give us optimization quite high. Basically, this goes down to, okay, so again, we have the same summary text. So this is the same text, same summary. And our time this time is 27 seconds. So out of the box, getting the better transformer from Optimum library, it basically, we have a performance boost, and definitely this can help us utilize AI capabilities in our LLMs in our application that we want to build. So the next thing is, so this is completely out of the box. So the next thing is how we can use more on a different accelerator. How can we use more, let's say, more performance boost to get even more speed again, and basically even decrease the model size? It's definitely a big thing and big deal. So for this, we're going to use ONNX accelerator. Basically, it's you can Google ONNX. I mean, it's pretty good accelerator, and a lot of the big companies are standing right now behind the whole let's say standard right at the moment. For example, like even IBM, Intel, and every single day the new company comes and they're supporting the ONNX. I mean, you can see you can have more transformers. You can use more accelerators. For example, you can use Gaudi, Intel's accelerator as well. So basically, you can play a bit with that and see what exactly matches your needs. So for this use case, we will cover text classification with this model. So this is the Stillbird Amazon shoe review, and we want to classify reviews by stars. So we will go from 0 to 4, basically from 1 to 5 stars. And we're going to evaluate the pipeline. So here we're going to do a bit of benchmarking to see exactly how fast is our pipeline in predicting our tasks. So we're going to use evaluate pipeline. This is from the library of scikit-learn, and we're going to use it for metric accuracy to measure that on our data set of this one, with this label calling labels, and this is the label mapping that we're going to use. And then we are going to evaluate our pipeline that we created here from vanilla transformer pipeline for our text classification and model ID. So I'm not going to run this because probably, I mean, not to waste time. So I'm going to just give you the results, but after you have the source code, you can run it yourself. This was basically ran on a EC2 instance of C6i instances, and I used the C6i extra large instance powered by third generation Intel Xeon CPU, codename Ice Lake, to see basically to get the results from that one. So the original model, when we evaluate that, it took 254 seconds to evaluate the model with accuracy of 0.57. So the next thing was, okay, so what we want to introduce from our ONNX and to get the better performance using the accelerator. So first thing that we're going to try is out of the box to use our ONNX runtime and use the ORT model for sequence classification. And we're going to call it and use it from pre-trained model that we selected here. And we're going to say from transformers true, basically set up our model for sequence classification. We're going to save the model in tokenizer as a new basically model in tokenizer. We will not going to change tokenizer, but model is going to be changed. So we have the first model that we inserted, and now we're running this optimizer on our model and basically saving a new version of our model that we're going to evaluate. So we're going to call the pipeline again from the task type and our model with the new tokenizer and model. And then we're going to evaluate our pipeline on the new pipeline that we set. And we basically can get something around 182 seconds. That means we've out of the box just converting a model and using a ORT model for sequence classification and just converting a model to basically optimum-based model with ONNX, we instantly get the performance boost here. Next thing that we can do is introduce ORT optimizer. And what we can do is with ORT optimizer is we can again call it from pre-trained model and use it to optimize and put it on optimization level of 99. And this actually means we can we're going to use all available optimizations on our model. I mean, you can if you want to use less, more conservative approach, you can use 1 or 2 or 5. But if you want to include all the optimizations, then you can put 99. And then we're going to save our model that we optimized again to our directory. And then again, we're going to call ORT model for sequence classification. We're going to use from pre-trained, and then we're going to set this new model with another file name. So basically, from the ONNX model, we are coming to a optimized model. So this one was out of the box. We created model ONNX, and here we used the model, and then we did basically applied optimization with ORT optimizer, and then created the new model that we're going to use, and we're going to call it model optimized. And here we're going to evaluate the pipeline with model optimized. And then you can see that here we can get something around 158 seconds. So we have a performance boost definitely here. Again, speed, giving us more, let's say, time and more power, faster dealing with the problems and tasks. So the last thing that we can cover here is to use the quantizer from the ONNX runtime. And this is basically the biggest improvement that we can get. So the purpose of quantization is to get the better performance in reducing the size of our model and still have the same accuracy. So the whole point of all of these tasks is our accuracy needs to be the same, and we measure the accuracy here. We said that we are evaluating the model for metric accuracy. So when you run it, you will see the accuracy remains the same around 0.57. So it remains the same, but model that we have the performance, we get the speed. And in this last thing, we can see that we even get the reducing size, which is quite big, quite big deal. So we can use ORT quantizer and call it from pre-trained model that we have. And then we can use the configuration for our quantizer, and we can use AVX 512 VNNI. Basically, you can play with it, play with this configuration. This really depends on what hardware are you running the whole optimization process. Here, because we're running on the Intel Xeon family, this is basically vector instruction set that we want to use to get the optimization for this type of the CPU. So if you're running on a different hardware, then definitely you will need to think about and go to the little bit of research about what kind of configurations you can get from quantization, and then put those configurations so you can get the maximum performance out of that. So we can call quantizer, quantize, save. We can put a save directory, basically where our model is, the first one. And then we are going to use ORT model for sequence classification and create a new model from our first model model ONNX and call it model quantized. So we're using pretty much the same principle as here, but here we're using the first model, and then we are pulling it through the quantization process with vector instruction set, and then getting the final model, which is quantized and then basically improved. So when we call this, we can see them in really huge difference with speed. So we can see that 66 seconds took to evaluate this model. And the good thing is that accuracy remained the same. But if you take a look, you can see that even the model size really reduced, because we use the optimization process with vector instruction set. So we get the really big difference with size of a model, which makes huge difference when you're dealing with AI and you want to save time and saving the size, meaning that you'll even save time here. So as you can see in this example, the performance boost is really high. So that was the last example. So definitely, I mean, you can take this source code that you have shared and try it yourself. So and how you play with it, just try to think about all different configurations that you can get, especially bear in mind the hardware that you are using, and do go for documentation of configuration of quantization and check exactly what are the configurations for different hardwares, so you can get the maximum out of your hardware that you're using. So even if you're using, for example, GPUs, or if you're using CPUs, doesn't matter. I mean, still you can research a bit and go through the documentation exactly what's the best configuration for your hardware to get the maximum acceleration that you want. So that would be the last example from my side. So from here we can go and cover the other part, which will Daniel now do. So I'll stop screen sharing so Daniel can go on and share his screen.
Okay. Let me set up the presentation and I'll share my screen. So let's do this. Slideshow. Well, how about I first share my screen? Let's see. You guys see my screen?
Yeah, perfect.
All right, sounds good. Okay, so first of all, thank you, Stefan, for a good review on transformers architectures and some basics of how we can optimize them. Of course, we are just scratching the surface here, but it's definitely good to see that some of these libraries that are publicly available, such as Optimum from Hugging Face and similar, the engineers have worked around the clock to make sure that out of the box they can achieve pretty good acceleration as opposed to just a regular basic implementation. So continuing on, I would like to introduce a different type of architecture called diffusers, and they are basically more focused on vision applications rather than transformers, which are typically for language processing, although there are some versions of transformers such as vision transformers that can be used for vision applications. However, for generative AI in the vision space, definitely the diffusers are currently state-of-the-art architecture. So let me start off just by defining what they are. Diffusers basically are generative networks. They are used to create new concocted images, audio and video. For example, if you give it a text prompt, what kind of image you would like to system to generate, it will follow that prompt and actually generate an image according to the instructions you put in the prompt, which is pretty amazing. The architecture itself, the diffusion architecture, they're based on essentially gradually adding and removing noise to create realistic images. I'll cover just a little bit more under the hood, because I think it's important just to set the stage and also to understand some control we can have on the model itself, which could be used for optimization purposes as well. Of course, diffusers are all around. They are currently the main architecture used under the hood of many quite well-known applications, text to image, such as Stable Diffusion, DALL-E, Midjourney, and others. I'm sure there are more. I just listed the most popular ones. Let's actually just take a step back and look at evolution of diffusers. So before diffusers were introduced, they were initial architecture used for generating images. Those are architectures referred to as GANs, which is the generative adversarial networks. They're the first architecture that was used to generate realistic images and other generative data. The GANs are essentially based on generator versus discriminator approach. So essentially, you have something like a battle between the two networks. The way you train them, they're essentially, the generator tries to generate images in such a way they're obviously fake, they're generated from the generator, but it's trying to fool the discriminator into, thinking that it's a real image. And as they train, they get better and better and better. And after a very long time and very long training process, they get really good at it. So the the generator, which plays the role of a forger, generates a fake image, essentially, but it's so good that the discriminator is, at the end, it's really hard to tell whether it's gonna, guess right or wrong. So it's a very interesting architecture, and it's kind of like a precursor of generative AI in the vision space. But there are some issues, and things like it is kind of difficult to train, especially in the early stages. So it takes a long time to train. It takes a while to set up properly the training constraints to get the good architecture at the end, the good model at the end. They can be computationally expensive, especially during the training phase. They do have limited control of the output, so that's another kind of a drawback. The network typically, it's very loose in how it's going to generate the image that you ask to generate. And finally, it's prone to some glitches such as mode collapse. Mode collapse has to do something with, like, during training, you can not get the output diversify too much. It gets stuck in some sense, even though the input is diversified. So anyway, the newer architecture that was introduced, which is the diffusers, this is the one we're going to talk about, essentially improves on all these issues. So it's a more state-of-the-art architecture, and as I said, it's used in many commercial and publicly available text-to-image applications. So in this presentation, I'll focus on stable diffusion inference workload. So we're talking about workload optimizations, and I will introduce some of the optimizations for the stable diffusion inference workload. Okay, so going on to the next slide, did give a little bit of an overview here, just under the hood, how the stable diffusion inference actually works. So if you look at you know, the inputs, the input is well, the main input is really the prompt, which is the text, which is try to specify what your generative AI network, in this case stable diffusion model, should give you as an image. So how does it work? Really, it has several main components which makes this thing happen. The first component is clip, which is the text encoder. Actually, the clip itself can be encoder and decoder. And essentially that is like a neural network model which acts like some kind of middle ground between the text space and the image space. So it kind of creates like what's called a text embeddings. So these text embeddings kind of represent your prompt in a space which is more similar to the image space, if you like. That's kind of an intuitive way to describe it. So the first step here is really really take this prompt and convert it to this text embedding space. And this embedding space is actually here like a two-dimensional, you know, matrix or 2D space, which you know, it's going to be more representative of what this prompt is, but in the image space. So this is the first input, and the second input is just the latent, the 64 by 64, that latent space, which again it's a space. So it's not the image space per se, but it's a more compact representation of the image space. So the latent space is something like a more feature space of that image, and where the essence of the image is captured in the 64 by 64 latent. And it's you know, it's like, again, it's a two-dimensional matrix. But what's important is that this network works like essentially working with an input latent and the text embeddings, which controls how the noise gets removed. Essentially, this UNet is the main component of the stable diffusion model. UNet is because it has like a shape of a U. If you look at the actual architecture, it's a convolutional neural network based model. So it has like, you know, different layers, and then you have a very long layer followed by smaller and smaller, and then goes back to like a, you know, long layer again. So it has this like a U shape. In this case, what this network does is, like I mentioned, the process of diffusion, which is in this case tries to remove the noise from the noisy image into a higher quality image. But of course, this actually works in a loop, because in order for you to get a really human level, like the quality of the image that humans would appreciate, it has to go through several loops. And this indeed is what I was gonna mention here, is that this number of inference steps is important to control the quality of your output. And of course, this is something we're gonna vary to, you know, essentially make sure that we have the you know, optimum value for this parameter. And yeah, at the end, so what happens is this conditional latent is again 64 by 64 two-dimensional output. It gets better and better in terms of removing the noise. And in the final stage, when all these iterations are done, this latent gets converted back to the image space. So from the feature space back to the image space via this what's called a variational autoencoder decoder. So there's an encoder and decoder. This is the decoder part, which essentially decodes from the latent space back to the image space. And yeah, and then we can see the image. I was asking here, is this example sailboat painting by Van Gogh? And that's what we got. It looks pretty cool. Anyway, that was just kind of like setting the stage here, because we will play with these parameters, and it's kind of important to understand under the hood what's actually happening. As Stefan mentioned already, the Hugging Face is a good starting point. We definitely have many released pre-trained AI models available on that repository, and also with the many code samples, some APIs to quick check things, libraries for these optimized versions of the Transformers and Diffusers and pipelines to very easily you can implement a pipeline to demonstrate, let's say, stable diffusion model or many other available models. So this pipeline is quite nice when you start to very quickly check a model. So we will work here in this tutorial with stable diffusion model C1.5. It's not the latest one, but it is a good model. What I'm intending to do through this demo is to explore quickly some optimization techniques, such as, and both for CPU and GPU, such as choosing the optimal number of inference steps, precision. We can change from 32-bit to 16-bit and still retain a really good accuracy, but the inference speed will be improved quite a bit. Then a little bit more advanced, we can look into things like reducing dynamicity. So intuitively, what that means is that when you run a model, the graph for the model gets compiled, and if you have too many dynamic, let's say, inputs, or even within the network, some parameters that are dynamic, then the performance gets like a hit, because every time you change the shape or whatnot, the graph gets recompiled, and that takes milliseconds that add up, and you end up with slower runtime. So what we will do, he will illustrate how simple thing like just setting the shapes to be static. Just say, okay, we're always going to use this, let's say, sizes of the input vectors, of the input tensors, can improve performance a lot. And finally, some architecture-specific optimizations that are really done under the hood, but we'll show how they play out. I think Stefan already managed to show with the ONNX some of those types of optimizations, but yeah, I'll also show some. So enough said. I will now switch to my actual, the systems that I have set up. So just briefly about the setup. So set up actually four different things here. One is a Intel CPU. So it is a powerful CPU. I purposely choose that one because otherwise, it can take a long time to run things on CPU, especially the heavy vision workloads. But this CPU is quite nice. This is a Intel Xeon Sapphire Rapids CPU. We can check this what it has. So this CPU here is let's pull up a little. Yeah, this is the it's a 2 GHz CPU, but it has a lot of cores. Actually, it has 52 physical cores. It has one socket, but it has 2 threads per core. So total number of logical cores is 104. So we can actually run many parallel processes. The more cores it has, for the vision application, for AI workloads generally, it is better than just having a fewer cores, but with the higher speed. So this is actually useful for running the deep learning workloads. And what we can do as a first step, what I wanted to say is also that to run this on a local machine, we need to install obviously all the libraries and other things. But the most important libraries we're gonna work on here is just like this. I'm gonna show what they are. Yeah, basically the torch, the torch vision, transformers, diffusers. That's the key one for us. And there's some other ones, the optimum and others, because I wanted to show you some optimizations with the optimum library for a CPU. So I actually don't have any code. This is kind of a live demo. So what I'll do is I'll go here and create a, let's see. All right, so this is this Hugging Face page. On this Hugging Face page, you can choose a model. In this case, we have a stable diffusion version 1.5. There's a nice API here. You can check the demo running on the Hugging Face servers. So probably it's going to run on a GPU, and we don't know yet, let's say, how many iterations they're going to do under the hood. But if we can type in and click compute, it's going to generate the image here to demonstrate. But of course, what we want to do is bring the model locally to our system and run it locally. So this is like a snippet of the code, which we can copy and try to adapt for running it on CPU. So if I go here and create like something like a new Python file, sd.py, and paste what I just copied, really what it does here, it's very simple. So from the diffusers library, it imports the stable diffusion pipeline, and then this pipeline is really simple to set up. The only thing really we need to say here is the model ID. So in this case, this is the stable diffusion v1.5. And yeah, okay, here we don't have to specify here. It's gonna go to default. I think the default is FP32. So we can, like, let's say set FP32 as the first thing. And the second thing we can change here is going to be, we're gonna push this pipeline onto the CPU and run it on a CPU rather than a GPU. And the prompt we can change as well. I just want to give you some intuitive thing about the prompt. So the more you write, the more specific you can get, and the more specific the image hopefully will be. But if you write, the more you write, the intuitively you should give it more iterations to run to actually give you a high quality output. If you give it a few iterations, it won't achieve that level of quality that you may want to have. Of course, it all depends on the application. If you're just running some, sketches like a first draft type of thing, then yeah, you can have a very small number of iterations, then you can see some sketches of how things could look. But generally speaking, for a production level or something like that, you want to have a larger number. So what is a larger number? Typically, people recommend something like 50 iterations. It's like a optimal. 100 or more would be like for some really long prompts, and something about maybe 25 or so would be for a more if you prefer speed, you can set it, let's say, to 25. Especially you can set it if your workload is something like animation or painting that doesn't require too many details, and then that 25 number could be good number to start. So let's actually do that. So in this case, I can say, let's say sales ship. Let's say sales ship or sailing ship, I think. Sailing ship in a storm by Van Gogh, let's say. It's one of the examples I was trying just earlier. That was pretty good. And okay, so here in the prompt section, I can define the number of inference steps. So let's say to 25. If we leave it by default, I think it will be 50. But let's say we just want to do 25. And we're going to save this image as, let's say, ship.png. So at this point, I think we are ready to go, except what I also want to do is add some timing because we want to measure the performance. So let me import some time. And let's see here, we can say T0 equals time dot time function. This gives you a number of seconds. T1 equals time dot time. So if you do the difference of the two, we'll get, except that's not what I want to put it. Sorry, this is where I want to put it. That's good. This looks good. So essentially, we're climbing this pipeline here, and let's print out that number, whatever that is, T1 minus T0. So here, this will gonna end up with measuring over time to generate image. Okay, so I already installed all the things. Of course, if you don't have it installed, you can just do pip install -r and then the requirements. And if I do that, it will just tell me that I already have everything, which is good. And second thing I did is I already ran this model, so it's cached. Otherwise, we would have to wait for it to pull the model from the network, from the Hugging Face storage, to pull it locally and run it locally. So right now it's already cached, the model, so we should be ready to go. So Python sd.py. And now this should run our inference, right? So we see here it's running the 25 iterations or inference steps, I'm sorry. So after it's done with it, it's going to print out. Okay, so it took 14 seconds for the 25 iterations. All right, so, and we can check how this is just on a bare metal. Let's see. Okay, yeah, so here's the image. I can kind of show you. So yeah, not bad. This is kind of the Van Gogh image painting, right? Of a sailing ship on a storm. So it looks kind of like Van Gogh. So it's pretty cool. All right, so as we can see, 25 iterations is probably okay for something like a painting. All right, so next thing we can try to do here to improve things would be to change the so this is on a CPU. So what we can do next is change the precision. So precision right now was set to, let's say here, yeah, it's set to like 32-bit float. So instead, we can do a 16-bit float. I think for this CPU, we can even use the BF16, which is the, so there are two types of 16-bit floats available, depend on your architecture, and they differ in a number of bits. They're assigned to exponent and mantissa. I believe for the float 16, we have about, I think we have 1 sign bit, 5 exponent bits, and 10 mantissa or the fractional part bits. But turns out there's a better representation, which is the B float, the better float, 16, which has one signed bit, it has eight exponent bits, and the rest, which is 7 bits, will be mantissa or the fractional part. So this turns out to be more suitable for deep learning applications. So that's actually good that we can use that. And so if we do this, now we can run it with a lower precision. Hopefully the quality will still be pretty good. I think it is because I checked, but let's run it anyway. Python sd.py. So 14 seconds with a FP32, and let's see it. Maybe a little bit. 12 seconds. Okay, so it wasn't like too much, but every time you run, it's a little bit different. So who knows? It's typically like doesn't scale exactly halfway, but it's in this case it wasn't a lot, but it's okay. So what we can do next, now instead of just blindly doing the the precision-based optimization, what we could do is we could now pull up and use the OpenVINO based optimum Hugging Face library, which already under the hood, it has a lot of optimizations done for the Intel architecture. And if you look at this CPU here, let me do this again, LS CPU. This CPU actually supports AMX, which is really really good because one of the latest extensions for the advanced instruction set that can essentially speed up your convolutions in the CPU in a nice way. So to take advantage of that, we could actually use this OpenVINO version of stable diffusion model. So, or rather, the pipeline. The model is still the same, but now we're applying the pipeline. To do that, there's a very simple thing we could do is essentially, I believe we need to, 1 second, I gotta check my notes. Yeah, I think we need to include one extra thing here. 1 second. Yeah. So this is not using a diffusers library from Hugging Face, but this time we gotta use the OpenVINO optimum library. So optimum Intel OpenVINO. So optimum Intel OpenVINO has this pipeline called OV stable diffusion pipeline, and that is quite similar to the pipeline that was implemented in diffusers. But like I said, it has under the hood some things which will point to different kernels different ops that are specifically designed for the CPU architecture set that you're running. So let's see, OpenVINO stable diffusion pipeline. Let's see, I think float 32, we can start with that. And the only thing I have to add here is export equal true. Export, yeah. So what's happening here is actually we're gonna take the model from the Hugging Face. We're gonna run on it some optimizations, and then use the optimized model with this library OpenVINO Optimum, and it should give you a good speed up. Yeah, I think everything else should be the same. So we're still going to run 25 steps, and let's see what happens. So, okay, so now it's essentially doing some. Okay, so these are just, you know, under the hood things. There's some warnings, but doesn't going to impact much. Yeah, we could probably, you know, ignore them for what it is. So essentially, it's trying to do some optimizations first on the model, and when it's done with that, it will do the inference on it with much more tuned operations under the hood. Okay, so compiling, so it's recompiling this model, and okay, so it's doing now inference. Okay, so so remember we did like something like 14 seconds and whatnot with the runtime with a regular diffusers library, and now we are achieving something like 10 seconds with actually doing 26 iterations, because this under the hood is doing one. I guess is doing this number of iterations plus one. So to be more fair, I could actually do here 24 to actually run 25 of them. And let me also change the float to float 32 to BF16, and let's see what that gives us. This would be kind of even more improved version of it. So Python, I could just sorry. Yeah. Okay, so it has to do recompilation again, because it I changed the precision, so it's gonna have to do a little bit different, you know, ops. Yeah, so we're expecting it to be improving, and we'll see how much. Well, this is the perks of doing the live demo, right? You gotta wait a little sometimes. But you know, I think it's good that we actually do it from scratch to show the process. Okay, so it's running here 25 steps. So okay, so I did it in a 9.9. Expect a little better, but you know, like I said, every run is different. But on average, you'll get more boost, I think. So because I think we still have, I wanted to also go and do some GPU runs. So I set up here 3 different GPUs. I don't know which one. Well, obviously we can check. This is the RTX NVIDIA 2080. So we can check this guy. Here, yeah, we can see that this is the GPU here, RTX 2080, 8 gigs of memory, of GPU memory. It's a little bit older GPU. For this kind of workload, we can probably use a newer one to get the real boosts, like A10 and A100 would be a good choices. Well, the A10 would be, let's say, how many NVIDIA SMI? Yeah, this is NVIDIA A10 card. This one has 24 gigs of GPU memory, so this should be a good one to try. So let's try this guy. I can just, first of all, let's see, I do have the requirements here, which I already installed, but let me just double check. Pip install -r requirements. Well, that's not command. Pip, yeah, I did already install them, good. I can just kind of copy this code. This is already CUDA code, so not much to change. SD.py. Not much to change, except we do want to limit our, this is float 16, we can leave float 16. That will give us the most speed up. Sorry, not here, but here, we're going to put a number of inference steps. $25, let's say. And yeah, let's put back the ship demo. Our prompt would be what I already put over there. And I can just copy from there to be exact. Here. Yeah, let's copy this guy. A10. Oh, actually, let's see the difference between 32 and a 16. So this will be like, I think the speed up of 32 is a default, I think. So this would be if you don't specify. Sorry, Python. Missing a T. Oops. Okay, so now we're running it on A10 card. This is a GPU, so we should get much faster. Yeah, we already see this is the fast. Oh, except I didn't put the timer. That would be useful. Let me quickly do this. Import time. Speaking of time, Stefan, how much time do we still have here? If you can hear me. I guess not.
You have a half an hour.
Half an hour? Okay, that's plenty.
Actually, 15 minutes. Sorry.
Oh, 15 minutes. Okay, that is.
Your tutorial is the last on this track, so if you need more time, it wouldn't be a problem. Okay, no, I think we're kind of close. I wanted to showcase a couple of different GPUs, so yeah, I think we'll have time for that. Yeah. Okay. So yeah, and here, let's say we are measuring time. So the last thing to do is print, you know, the time difference. And yeah, this is it. Python sd.py. So this is the same thing we ran earlier, just going to show us the timing. And all right, so we are now at 4 seconds, so it's quite a bit of a speed up. This was with 32-bit precision. We can even think we can peak at let's see, where's the yeah, here is 32. So let's try 16. This will be out of the box. Okay, one note. I believe that on this card,
The BF16 is not available, but the float 16 is available. So let's use that one. And run it. Okay, I think it's running. Maybe not. Oh, it's running here. All right, so this is much better. So yeah, this is good. Now we're only two seconds pretty much. It's what it took to run 25 inference steps to generate the image. Is a good. It's a good user experience if you like. We can try the same on the other cards just if we have some time. So yeah, so again, you have to take in consideration a cost, what's available to you, you know, all that. For example, this card would be, I don't know what it is right now, maybe $500 or something like that. So it's like a lower end at this point because it's been a while. This is an older card. A10, for instance, is still pretty new, you know, a pretty powerful GPU. This one is maybe around 2.5K, let's say. And A100, I don't know, it's probably like 5 to 8K, depends where you buy it. So it's depends on the cost, right? So I don't know what it is when you rent it on the cloud service, whichever cloud service you have. If you use that, I'm sure these cards will be wouldn't be cheap to rent. So yeah, maybe running it on a lower end card for this kind of models is okay, and we'll see that. And you can even run it on CPU. Of course, it will be slightly slower, but we managed to get about, let's say, 9-second performance on a CPU compared to, I don't know, 2 seconds here on this very powerful GPU. If you go back to like older version of the card, RTX 2080, we can try to run it there. I'm just gonna copy shamelessly what I already have created here to the other GPU system. Yeah, that. Guess I already have it from before. Yeah, I think this is basically the not quite the same. Let me get rid of this guy. Just copy the exact. I think this one runs 50 iterations. That's some like yeah, it's identical code. Let's see what it does. And this will be 16 bits precision running on a GPU RTX 2080. And yeah, really close to what the A10 did, which is pretty amazing. I mean, okay, this was more like 2.2, which is comparing it to 2.8. So it's not a big difference at the end of the day, unless you have to do a lot of inferences for some whatever application you're doing, or as a part of some system that uses output of the stable diffusion to train, in which case this makes a big difference when you do like a large scale training. A100, okay, how about there? Let's create the same file. Oops, not quite what I wanted to create. Yeah, that's the one. Okay, and this is the ultimate GPU experience, except if you have H100 or H200, but that's a bit hard to get. All right, so look at this. A100, it's worth the money, huh? 1.3 seconds, it's all it took to run this pipeline. Okay, I think that's kind of what I had in mind to showcase. I didn't know exactly how much time it's all going to take, but I'm glad I managed to squeeze within the allocated time. I don't know, Stefan, do you have any more closing remarks from your side? Or does anybody have any questions? If I don't know if this call we can ask questions or not, I don't know.
Yeah, basically nothing from my side, more so Emilia. So are there any questions we can answer, or what's the...
One attendee asked, can you share a link with materials? But you already shared it, so.
Stefan, you have that right available for people.
Yeah, I share the link. I mean, not the link. I pasted. So.
Yeah, you shared the materials, so.
Okay.
Okay, thank you very much, Stefan and Daniel. This was very interesting, and we're glad to have you as our tutors.
Thank you.
Thank you, Emilia, for inviting us.
It was a pleasure. Goodbye.
All right, bye.
Thank you. Bye.